Good morning, all. Is my screen visible?
Yes, sir.
Okay. So yesterday we saw elements of visual perception, uh, the meaning of which is which things matter in analyzing or understanding an image. So the things those matter are actually a structure of an eye, how image is formed in the eye, that is the number of holes, number of rods available, and what is brightness, adaptation, and discrimination of that particular viewer. How we can identify the separation between colors and separation between the glare, the brightness, and the darkness. So we saw those three things, and then we talked about the simple image formation model, in which I told you that the image is basically the intensity f at a coordinate x comma y, and that intensity at point x comma y is dependent on incident light at that point multiplied by the coefficient of reflection at that particular uh, area on which the light is incident. So depending on the type of substance on which the light is incident, the reflectance will be different, and hence the f will be different for different materials, and accordingly we will see the different amount of reflected light from the scenery, and that our eye considers as a image. We saw some examples in last lecture that the reflectance is more for the snow, and it is very less for the black velvet, and because of these different reflectance properties they can be easily identified with different intensities. Here I included one additional slide to make you understand what a single image sensor looks like. This is a single image sensor. Here you can see that the light energy is incident on this sensor part. The sensor is made up of one uh, photoelectric cell, you can say, on which the incident amount of light energy will be converted to the electric voltage. So there is some sensing material, there is some encasing or housing, and there is some additional power required, because that is not a passive source. Additional power is required. For example, a camera may not work if we do not use cells or uh, dry cells or any other kind of power. So some kind of energy should be provided, electrical energy should be provided to energize this, and then when the photons are incident, electrical voltage will be generated, and that will be carried to the processing unit. So this is a single image sensor. Single image sensor means what? This is a single device which can identify only one intensity level. So if I have this complete image, then at this point I can use one such sensor to identify the intensity at this level. And to identify the intensity at this complete line, I will have to arrange more of such sensors in horizontal arrangement like this, and that is being shown here. They will have a parallelly connected input power. They will have a parallelly connected input power, which is shown on the left hand side, and um, the parallel output of each of these block will be used and provided to the processor, and individually intensity at different points will be sensed, and this is called as a line sensor. And to cover the complete image we need more of such line sensors. So when actually image is formed, the light is incident on multiples of such single sensors which are arranged in a horizontal and vertical manner, which will have a common power input which is parallelly connected or shorted internally, and they will have individual output voltages which are arranged in such a way that the processor can easily recognize which line corresponds to which blocks. Okay. Then we yesterday started with the image sampling and quantization, where I told you that suppose I want to uh, convert this continuous image or actual natural scene to the digital image, then what I have to do is, suppose I'm talking about only one line, that is line passing from point A to point B. Then I told you that here we have a very white color, that is bright light. Here we have bright light. Bright light corresponds to intensity level high. So this is a intensity level high. In between this point and this point, that means this point and this point, we have varying intensity level. So as we go from this side towards center, the intensity level increases. Similarly, as we move from this side to backward, the intensity increases. And at center somewhere, you have the largest intensity. The largest intensity is available, but it is not comparable to what is intensity at point A or what is intensity at point B. So at A, you have the largest intensity, and at center, you have little small intensity, but which is more than this region. So you can generalize and you can sketch some graph like this. The intensity at boundaries is less, and when you come near center, the intensity increases. But that intensity is much lesser than the intensity at point A and B. Okay. So I sketched some relevant graph. Now you see that the intensities here are varying continuously. If I want to convert each and every individual intensity value to the binary number, then I will have to use infinite number of bits, because there are infinite intensity levels. So I will first convert, uh, and also this is a continuous graph, that is in a spatial coordinate. You have, uh, suppose this is a line A to B. If you want to represent that line A to B, if you see how many different points are there or pixels are there, you will see that there are connected pixels. Connected pixels means what? You cannot easily count how many number of pixels you have. So I can say that in a continuous graph, there are infinite such pixels available. And if there are infinite number of pixels available, or if it is a continuous graph, computer or any processor for that matter cannot process that data, because computer or processor is a discrete machine. So let's first discretize this graph in a spatial domain. Spatial domain means what? In a space coordinate. So here we have infinite number of samples. Let's say consider the sample at this point, this point, this point, this point, and this point, and this point, and so on. So we will consider samples located at equidistant positions, just to make it a discrete graph, and that is called as a sampling in a sampling in a spatial domain, and that will result in those small squares that you see on this particular graph. The small squares that you see here is because of spatial coordinate sampling. After that, we get some intensity levels. So as you can see, still there are some finite number of intensity level possible for a complete image. This is what we are talking about, is only set of samples between point A and point B. If we analyze the complete image, you can see there are a variety of intensity levels available. So we again cannot represent those intensity levels with finite number of bits. So to store them with a finite number of bits, we will make only finite number of intensity levels, and that is called as quantization of the intensity levels. We have infinite, see, first step is we have infinite number of pixels, we sample and we make finite number of pixels. Next step is we have infinite number of intensities, we quantize it and we make finite number of intensities. So what we generally do is, suppose I want to quantize into eight amplitude levels or eight intensity levels, then I will mark those eight intensity levels like this. Like this, I will mark all those intensity levels, and whatever intensities fall within this boundary, whatever intensities fall within this boundary, I will treat them as a only one intensity level. So you can see that this, and these three pixels are considered to be of same intensity. Actually, if you observe here, these three pixels are of different intensity. They have little variation, right? But while sketching the final graph, those three pixels are sketched on a single line. So all the pixels which are lying within range of that first partition, they will be treated as only one amplitude level. So you can see at the bottom there are two amplitude levels which are different, but while sketching I have sketched both of them on a single line. So as you can see here on a single line, isn't it? So now we have only fixed number of amplitude levels, that is only 8 number of amplitude levels, which can be represented if I use 3 number of bits, because 8 is equal to 2 raised to 3. So if I use 3 bits, then by using the binary number representation, I can represent these 8 amplitude levels. And this is how the processing is done in an image. We sample that image and we quantize that image so that the storage requirement is reduced and we can easily represent with finite number of bits. Let's go ahead. So as I said here, this is called as digitizing the coordinate values, or digitizing spatial coordinates, and this is called as digitizing the amplitude values, or digitizing the intensities. So finally, if you do that, then the image will look like this. So what basically I did is, each of these boxes will be considered as one spatial coordinate value, and the intensity of those boxes will be fixed between intensity 0 to intensity 7. That is only 8 amplitude levels, or only 8 intensity levels. So as you can see here in the original graph, the intensity levels are infinite. Also, the number of pixels available are infinite. But now I decided that this will be a size of a pixel. I decided that this will be a size of a pixel. And then I decided that the size of so then I decided that a single pixel can have the intensity value, which can be any one intensity out of the total 8 intensity levels. So I finalized that there cannot be any intensity other than 0 to 7. So this way, if you observe this graph, the amount of intensities which you can observe cannot be more than 8. You can have only 8 intensity levels. So further, if I use larger number of pixels, that means instead of using this 1 pixel, if I use 4 pixels here, if I use 4 pixels, then I can have more accurate representation of this graph. Further, if I have, instead of 4, if I further divide, and if I make 4 here, 4 here, 4 here, and 4 here, so total 16 pixels out of that single pixel, then that will give me a further better approximation of the actual image. And the way increase the number of pixels is basically I'm trying to increase the resolution of the image by adding number of pixels to represent the same graphical area. Okay, so the first one is the original continuous image, and second is the result of image sampling and quantization. Please type in a chat box whether you understood this. This type of sampling and quantization you also can observe if you zoom in into some black and white image to the maximum possible limit. You will be able to see this kind of checkerboard patterns. Please type in the chat box whether you understood. Manjunath Bhave has understood. Okay, let's go ahead. Mayekar Rigved also understood. Very good. So the resolution that I was talking about are of two different types. One can be the spatial resolution, where the number of pixels are increased, and the other is a tonal resolution, where the number of intensity levels are increased. So in a previous graph, you see I have used only 8 intensity levels. Instead of 8, let's say I use 4 bits to represent the data, and hence I will have 2 raised to 4. is equal to 16 number of intensity levels. Here I use 3 bits to represent data, right? Here I use 2 raised to 3 is equal to 8 intensity levels. 8 intensity levels means 0 to 7. And now I am trying to use 4 bits to represent the data. So I will have 16 intensity levels. 16 intensity levels means the intensity 0 to intensity 1, 5, 15. Okay. So if I use more intensity levels, then still I can get a good amount of detail from the image. See, if I use only 8 intensity levels, the transition from this bright color and this little grayish color is more pronounced. We can easily identify that. But if we add a range of gray color in between these two, if I add one more additional range of gray color in between these two, so I will have smooth transition from white, little gray, and then black. This kind of smooth transitions will be added in between all individual pixels, horizontally as well as vertically. So in between this pixel and this pixel, the intermediate intensity between these two will be added. In between this pixel and this pixel, the intermediate intensity between these two will be added. So everywhere this will be added. Additional intensity will be used to represent that same image, and that way we call that image is having a more tonal resolution. Tone means color tone or brightness tone. Okay, so tonal resolution means more brightness values. So we have number of samples in the digital image represented by capital N and number of gray levels represented by small m. More of these parameters are increased, closer will be the digitized array approximating the original image. So as I said, if you use more pixels with more intensity levels, you will go more and more close to the original image. However, the amount of memory space required to store that will be increased. So if you use larger number of pixels, you have to store and use large amount of memory. If you use larger number of gray levels, still you will have to use more number of bits to represent each individual intensity pixel, and hence you will have to use more number of storage, more amount of storage. So good image is difficult to define. As I said earlier, image processing is a very subjective topic. Every person can have their own opinion, and hence it is difficult to define, because the image quality is not only highly subjective, but it is also strongly dependent on the requirement of given application. So for certain application, a little poor image it's okay. Little poor image is okay. For example, in medical application where you want to detect some kind of bone fracture, a very good X-ray image is very necessary. But but in some other application where you want to identify where there is a person present within a room or within a car, it's an application where the actual boundary of a person is not so important. If the person is present, that is the only application, if the person is present or not. So in this case, good image is not so necessary. A poor quality image is also sufficient to identify. So it depends on application. The quality of an image is greatly varied by variation in the above mentioned factors. So again, the definition here, the number of samples of a digital image are changed as a power of 2, keeping the display area same. The meaning of this is, suppose this is an image. This is a 1 pixel of an image, for example. If I want to increase the spatial resolution, how can I increase that? I will have to use larger number of pixels to represent that same image. So instead of 1 pixel, now I will have to use 4 pixel. Why is it so? Because I already told you the pixel is having uniform size. The width and height should be same. So if I want to divide that earlier square box with smaller square boxes, then at least we should use 4, because if I use only 2, then they will give us rectangles like this. This is a rectangle. This is not a pixel. This is a rectangle. This cannot be called as a pixel. because pixel has uniform width and height. So to make it uniform, at least we should have 4 pixels within the previous area. So earlier we had only 1 pixel. Now we have 4 pixels. Further, if I want to increase the quality, what I will have to do? Further, I will have to divide each of these boxes with 4 pixels. So what will be total number of pixels then? 4 plus 4 plus 4 plus 4. So total 16 pixels are needed to represent the same image with high resolution. So in first representation, I use only 1 pixel, that can be called as a 2 raised to 0 number of pixel. In a second representation, I use 4 pixels, which can be called as 2 raised to 2. In a third representation, I use 2 raised to 4 pixels. And further, you can go ahead and you can see that we are always changing the number of pixels as a power of 2. We are changing the number of pixels as a power of 2, because we cannot randomly increase the number of pixels, because that will introduce the irregularity in the shape, which is not at all accepted. So the spatial resolution means increase the number of pixels by keeping the uh, same area and maintaining the same contrast, same constant gray level. So here we are not talking about any variation in the gray level. If you have 8 gray levels, use those same 8 levels, but use more number of pixels. That is called as spatial resolution. The pixel in the lower resolution images are duplicated in order to fill the entire display. This pixel replication produced a checkerboard effect, which is particularly visible in the images of lower resolution. So we saw here that if this is an image having uh, pixels with this size, if I introduce the image which has more number of pixels, then each of these individual pixels will be divided into 4 pixels, and accordingly the whole image will be having more number of pixels. And if the pixels are very small, very small, then the variation from color to color, like how we see here, this color is different, this color is different. But if we use 4 different pixels in each individual box, and then if I replicate them, then from pixel to pixel variation will not be so noticeable. And that's why here I said that uh, here that's why I said that the checkerboard effect is more visible in the images of low resolution. So if you have low resolution image, that means you will have more pixel size, that is bigger pixel size. And if you have bigger pixel size, then from big pixel to some other big pixel, color variation is easily noticeable, and that's why you can easily observe this kind of checkerboard effect. It's like a chessboard pattern with some additional gray intensity levels. And the tonal resolution, as we said earlier, is here the number of pixels are kept same, but intensity levels are increased. So the quality of image is varied by decreasing or increasing the number of bits used to represent the number of gray levels in the image. So as I said earlier, we can use 3 bits to represent 8 intensity levels, we can use 4 bits to represent 16 intensity levels, and so on. The effect on the image quality produced by varying the number of pixels and number of intensity levels are subjectively analyzed by the level of detail pertaining to the image. So it's subjective, as I said earlier, it depends on the application for which we are using those images. General conclusions that can be drawn from the subjective study are: in most cases, the quality of image tends to increase as we increase the N and M, and in few cases, the number of pixels kept constant and the quality is improved by increasing the small m. Sorry, this should be small m. So in a few examples, only increasing the amount of intensities will be sufficient. No necessary to increase the number of pixels. Another conclusion is for images with a large amount of detail, only a few gray levels are needed. See very carefully. For the image with large amount of details, only a few gray levels are needed. Increased gray levels for an image of a mob may increase the obscurity of the image. The uh, example for this is, suppose you are showing a very crowded area of a market. Imagine the scene. You are representing a crowded area of a market with a black and white color, or with a grayscale image. Grayscale means there are no any other colors. So if we use very few amount of intensity levels, that image will look better. Why? Because there is a crowd, and from person to person, every individual detail is not available. For means uh, that means the eyes, the nose, the mouth of that particular face is not so visible. Only the heads are visible, and you are looking at a image of a crowd. So if minor details are not so easily available, why to use very high amount of intensity levels? Are you understanding? So if you use very high number of intensity or gray levels in such a image, it will instead of making image good, it will make it worse, and it will increase the obscurity in the image. So for such an image where very large amount of details are there in the picture, very few number of gray levels are sufficient. So this is why I am saying that it is a subjective study. Means the person to person the choices may vary, and if you actually see an image of that particular crowd or mob, you will get convinced with what I am saying. You will get to uh, the same conclusion that if I have a crowd image, I should not use large number of intensity levels, because then it will be like only some gray shades here and there. You won't be able to see even person or market or what any other area. So the example of spatial resolution, as I said earlier, here this is a low resolution image. There are only 4 pixels. This is a medium resolution image which is having 16 pixels instead of 4. I am using now 16 pixels, and this is further higher resolution pixel. Uh, Instead of 16, I am using 64 number of pixels now. So very high resolution, and you can see that the checkerboard pattern or chessboard pattern, which is a rough variation of the intensity, is very easily seen here, but slight variations are seen only in the last image. So that's why I said the checkerboard pattern is less visible if we use a high resolution image. The spatial resolution is a measure of the smallest object that can be resolved by the sensor. Another definition of spatial resolution is how smallest object, or what is the smallest dimension of the object that can be captured by the individual pixel. For example, suppose this is an image. Some camera can capture one face in a crowd with a one uh, pixel. This is an example only, yeah? And some other camera, some other camera can capture one eye of that person with a one pixel. What I am saying here, the image is captured where one pixel is representing one face, and here one pixel is representing the eye of that person whose face is shown here. So here a little wider pixel is used to represent the image data. So if you want to get minute details from this image, it's not possible, but from this image you can get very minute details, because a pixel is of small size and it is representing even a eye of that person. Even a eye of that person can be seen. So here I can say that the smallest object that can be resolved by the sensor is of eye size in this case, and the smallest object that can be resolved by the sensor is of face size in this case. And then I can say that the spatial resolution is more here, because smallest object that can be resolved is here in this particular case, because eye is smaller than face. Suppose I have another camera which can focus so nicely that one dark black circle within a eye, one dark black circle within a eye will be represented by 1 pixel. So the complete eye is represented by, say, for example, some 8 to 9 pixels. Complete eye is represented by using 8 to. So which of these represents the smallest object? This camera represents the smallest object. So this is called to be having a good spatial resolution. I hope now you understood. So the another definition is the ground area image for the instantaneous field of view. Instantaneous field of view, IFOV. This kind of definition is generally used for the cameras which are mounted on satellites, because from satellite some cameras can sense uh, one vehicle on the ground as a 1 pixel, and some cameras can sense one big house as a 1 pixel, or big building as a 1 pixel. In this case, the instantaneous field of view of this camera is of size of one car, and instantaneous field of view for this camera is of size of one house. So this camera is better because it is focusing on the smallest object. Compared to house, the car is small, right? So there are a few other definitions. You can just have a look, and if you understood the meaning you can represent in your own language. That's not necessary to use either of this or this or this definition. You can use any one of them. In the book that I suggested, that is Gonzalez Woods, the definition is the spatial resolution is defined as the smallest discernible detail in the image, which is same as the smallest object that can be resolved, right? So there are little variations in the definition, but the meaning is same. So when you talk about smallest detail that can be viewed from the image should be of same size. Then only you can compare the spatial resolution. So here you see that the first image is of dimension 227 cross 222, the number of pixels horizontally and vertically. And the second image has horizontally 980 pixels and vertically 749 pixels. So if you are having these two images, you cannot compare the spatial resolution, because spatial resolution is all about the number of samples in a specific area of the image, as you can see here, specific area. So if the area of two different images are different, we cannot compare the spatial resolution. So if you want to compare the spatial resolution, the images should be of same size. And then by looking at that image, you can see that which of these image can give you a more discernible detail, which of this image can give you a smallest finite details. Obviously, this image can give you the smallest finite details, and hence the spatial resolution of this image is more than this image. I hope the idea is very clear now. Let's go ahead. The spatial resolution for multiple applications or multiple hardwares can be defined by or measured by using different ways. For monitors, it is measured by using dots per inch. Means how many horizontal and vertical dots can be displayed in a 1 inch size. Okay, and that's how the uh, DPI. That's how the monitors are using the unit for representation of the spatial resolution. So we see that the banner is printed with DPI of this or this. The meaning of this is in a 1 inch by 1 inch size, you will have this many DPI. This means, say, like for example, 720 DPI. So you will have 720 dots in a 1 inch by 1 inch size in that banner. If you print another banner which has 1080 dpi, the meaning of this is you will have 1080 number of dots. So generally for the monitors we talk about dots. For digital displays we talk about pixels. Each of those dots are nothing but smallest possible element in an image, which is called as a pixel. So this terminology is used for the digital image, right? For laser printers, the terminology used is lines per inch. How many line pairs can be printed in a 1 inch? That is called as lines per inch. So if lines per inch are more, that means you can have a more better spatial resolution. And we have already learned this pixels per inch for the mobile phones or top tablet devices. How many pixels per inch we have, that will define the uh, spatial resolution of the digital device such as a mobile or tablet. And tonal resolution we already learned, it is simply the varying number of gray levels by keeping the spatial resolution constant. So we can have black and white image where levels are in between black and white we can see the shades of gray, and those shades of gray we can have more number of gray levels to increase the tonal resolution. That's it. There is no much discussion available here. In color images also we can have specific color use. For example, red color also can have very less intensity to very high intensity. Okay, so red color, single color itself can have the varying level of intensity. So the general rule is tonal resolution for the black and white picture information should be at least 8 bits. Meaning of this is, if you have a black and white image, then to have a better image, you should at least use 8 number of bits to represent colors. So how many total colors you can have? You just count what is 2 raised to 8. Those many number of gray levels are necessary, and the number comes around 2, 5, 6. And that's why I said that uh, zero intensity level represents complete black color, and 255 intensity level represents a complete white color, and in between there can be other gray intensity levels. So this is the minimum requirement if you have a grayscale image. Otherwise the image will look dull. The tonal resolution for full color pictures information should be at least 24 bits. The meaning of this is, if you have color image, I already discussed multiple times that color image is made up of red, green, and blue colors. Most of the time, this is the color model is used, which is RGB color model. So red color can vary intensity from 0 to 255. Green color can vary in intensity from 0 to 255, and blue color also vary from 0 to 255. So this is represented by 8 bits. This is represented by 8 bits, and this is represented by 8 bits. 8 multiplied gives you 24 bits. Sorry, added together gives you 24 bits. So there are three different color planes, one for the red color, other for the green color, and third for the blue color. Together they carry 24 bits for the color image, minimum requirement. So how many total number of colors you can have? 2 raised to 24. Out of which, one third part will be shades of the red color, the darkest red to brightest red. Remaining one third will be of shades of the green color, and remaining one third will be shades of the blue color. So total number of colors available are 2 raised to 24. This comes a very big number, and we have heard that number, the true color or the million color, 16 million colors available for the display of the television screen, 16 million colors. So those are actually derived from this calculation. And actually Actually, this 2 raised to 24 does not mean only one red or one green or one blue intensity. It is combinedly RGB. So when you combine red of some intensity, green of some intensity, and blue of some intensity, you will get uh, the resultant color of some specific intensity. We will discuss this later again. I already told you that the image is a intensity at coordinate x comma y. So it is represented like this. The origin will be at the first left, top left corner, and the y coordinates increases in the right side, and the x coordinate increases downward. So the intensity at this point will be read as f of 1 comma 0. Intensity at this point will be read as f of 0 comma 1. I hope you will remember this. I read image pixels 00, 01, 02, 03 in the first line, and I read image pixels as 10, 11, 12, 13, and so on in the second line, 20, 22, 23, 24 in the third line, and so on. This is the same representation. We have a array of m cross n where there are m number of pixels in the single column and n number of pixels in a single row. So total dimension of image is m cross n. Each of the pixel, as I said, each of the pixel is represented by some eight number of bits in the earlier example that we took. So in general, we can say we have L number of levels. In this case, in the previous case, we said that there are eight number of intensity levels. So to represent that image, we need 2 raised to 3. That means 3 number of bits. So here k is equal to 3. This is a specific example. In general, we can say that there are L intensity levels with each intensity represented by k number of bits. And as I said, here we have m cross n number of pixels. So total number of pixels are m cross n. Each pixel is using k bits. So this will give us a total number of bits used for the image, storing that image. So b number of bits are required to store an image, which we can find as total number of pixels multiplied by the number of bits used for the single pixel. So single pixel has the intensity represented by 3 bits. It can be in between intensity 0 to intensity L minus 1. In this example, if you are using 3 bits, then intensity 0 to intensity 7, right? So the number of pixels multiplied by number of bits per single pixel, that will give us total number of bits for the image. Small discussion here. We can see here these 3 different images. We can have a black and white image. The better version of that is increase the intensity values and introduce the grayscale image. I hope you can see that and you can conclude that grayscale is better than black and white. Further, you can use 3 different intensities of red, green, and blue colors, and collectively, if I look that, that will be formed as a true color image, and it is a color image basically, which is further better than the grayscale image. So in a representation of this to this, black and white to gray, we have further choices. We can use lesser number of intensity levels. We can use further higher number of intensity levels. We can use more number of then more intensity levels, and accordingly, we see that as we go ahead towards right side, number of intensity levels, the picture becomes more and more better. So here, this is the image which is represented with 8 bits per pixel. That means 256 number of intensity levels, and that is a better image. Further, you see that here this image looks more better than this. Why is it so? Because it is using 256 intensity levels. This is also using 256 intensity levels, but the overall intensities are moved towards the brighter side. So all the pixels having some intensity, all of those pixels are increased by certain proportion in a intensity. It's like, uh, you people are giving some exam. You people got a score from, say for example, 40 to 60, and I decided that the 40 to 60 score is passing score, but it is not so good. So I decided that let's give a boost of 20 marks to everyone. So what will be new marks? New marks will be 60 to 80, and that will be this image. So this is actual image. This is actual image which has the intensity levels 256, but overall average of all those intensities is towards darker side, and I want the overall intensity of the image to be bright. So I give a common boost to all the pixel intensities, and then I got this. So this is the image which is having a lesser intensity, further higher intensity. Overall intensity is increased. Means what? I will give a common boost to intensity to all the pixels in the image. So this is the medium boost in the intensity. This is the largest boost in the intensity. If I give more boost to all the intensity levels, the image will become more and more brighter. That will not be so good to look at. Okay. You can see that these are the three planes which are available for the pixel: R, G, and blue, red, green, and blue plane. Intensities are only shown; the colors are not shown. I will explain this part again in the coming lecture. We will continue with the remaining part in the next lecture. We have the neighborhood and the color model that we will learn in the next lecture. If you have any doubts, you can ask. Otherwise, we conclude the lecture and you can leave it. Thank you. If you have any doubts, you can ask.